All right, welcome to another deep dive. You know how this works. We take your burning questions, grab the source material you send our way, and, well, we dive deep. This time, we're tackling something that I think is super relevant to, well, pretty much everyone.
Yeah.
Learning.
Yeah, learning, but with a bit of a twist, right? It's not just about what we learn, but how the tools we use, the environment we're in, even just the way we're thinking about a problem can completely change how that learning happens.
Exactly. You sent us this really cool article combining physical, virtual, and mental actions and objects. It's by Stephen K. Reed, and it's a bit of a brain bender, I'll be honest.
It does make you think. The whole idea is that it's not enough to just consider the content we're trying to learn. We also need to think about the actions we're taking and the objects we're using, whether they're physical things we can touch, digital stuff on a screen, or even just things we're imagining in our heads.
Right, because, have you ever noticed how sometimes just explaining something out loud helps you understand it better?
Hmm.
Or, building something with your hands makes it stick in your memory?
Totally. It's like that quote by Eric Weiner. Big ideas often come from unexpected places. That really resonated with me when I was reading this article. It all ties into this concept called situated cognition. Kirsch talks about it a lot. The idea that our thinking is deeply intertwined with our environment and the tools we use. It's not just happening in our heads, it's happening out there in the world too.
Okay, so that's the big picture. Our mission today is to unpack this whole idea of how physical, virtual, and mental actions and objects all work together when we learn. And the article lays out this really neat 3x3 framework to help us do that.
It's like a grid. We've got three types of actions: physical, virtual, and mental. And three types of objects, again, physical, virtual, and mental. 9 possible combinations, and each one tells us something really interesting about how we learn.
Okay, so before we get lost in the grid, let's make sure we're all on the same page. When we talk about physical actions, what are we really talking about?
Physical actions are, well, think about it like moving your body, interacting with the world directly, not just clicking a mouse or tapping a screen, swinging a golf club, doing a dance move. Those are physical actions.
Got it. So virtual actions, then that's where screens come in.
Exactly. Anything where you're using a digital interface, a mouse, a touchscreen, a controller to manipulate something on a screen.
And mental actions.
Mm-hmm.
I'm picturing daydreaming, right?
Sort of, but more specifically, it's when you're mentally simulating an action, rehearsing it in your head, imagining how it would feel.
Okay, makes sense.
Yeah.
And the objects follow the same logic.
Right.
Physical objects, the stuff we can touch and hold. Virtual objects, they're digital representations. Mental objects, the things we conjure up in our imagination.
Exactly.
All right, 9 combinations, 9 different ways of learning. Let's start with the most straightforward one, physical action on physical objects. This one feels like, well, just life, right?
It is. It's how we interact with the world most of the time. But even within this seemingly simple category, there are some fascinating nuances. One of the best examples is Montessori education. You know, they use all those physical manipulatives, blocks, cylinders, beads to teach math concepts.
Right, those colorful wooden toys.
Exactly. And it turns out there's real science behind it. A meta-analysis that's a study that looks at a bunch of other studies found that using these physical manipulatives has a pretty decent positive effect on how well students remember math knowledge.
So it's not just about making learning fun. It actually helps kids learn better.
It seems so. But here's the thing. That same meta-analysis showed that the benefits were smaller when it came to problem solving, actually applying that knowledge to new situations. It suggests that how we use those physical objects, how we interact with them, really matters.
Okay, so just having the blocks isn't enough. You need to use them in the right way.
Exactly. The analysis found that having a lot of instructional guidance, clear instructions on how to use the manipulatives, helped with retention, remembering the information. But sometimes, believe it or not, less guidance actually led to better transfer, being able to use the knowledge in new situations.
Really?
Ah!
Less guidance. That's counterintuitive.
I know, right? The article talks about this study by Martin and Schwartz. They were looking at students learning about fractions using physical things like tiles and pie pieces. And they found that if the manipulatives were too structured, like if the pie pieces were already cut into the right fractions, it actually prevented students from really grappling with the underlying concepts.
So if the answer is already there, you don't have to think as hard.
Right. But then when you encounter a new problem, you don't have the mental tools to solve it. So it seems like sometimes a little bit of open-ended exploration, even a bit of struggle, can lead to a deeper understanding that you can actually use in different contexts.
Okay, that's a good reminder for all of us, not just in education. Sometimes Figuring things out for yourself is the best way to learn. Now, let's move to the next combination. Physical action on virtual objects. This one feels particularly relevant in our digital age. What's a good example of that?
Well, I think a lot of us immediately think of gaming, right? Especially with the rise of motion controls and things like that. The Nintendo Wii is a classic example. You're physically swinging your arm, but it's controlling a virtual tennis racket on the screen.
Right. Or like dancing games where your movements are mirrored by your avatar.
Exactly. And what's really interesting is that research suggests that even those seemingly frivolous interactions can have a real impact on our behavior in the real world. The article mentions a study where people who played Wii tennis cooperatively were more likely to help someone who dropped pens afterward compared to those who played competitively. But here's the kicker. This effect was strongest if they had personalized their avatar, like chosen their outfit and stuff.
Wow, so feeling more connected to your virtual self makes you more helpful in the real world. That's wild.
It is pretty fascinating, isn't it? And beyond just gaming, this combination of physical action and virtual objects pops up in educational settings, too. There's this thing called the Mathematical Imagery Trainer, which uses motion tracking. So, as a student moves their hands physically, those movements control cursors on a screen to teach them about mathematical ratios.
So they're using their body to interact with these mathematical concepts, even though it's all happening on a screen.
Exactly. And the idea of attentional anchors comes into play here. The student is looking at the screen, focusing on the visual information, and that's guiding their physical actions.
Okay, so it's like the screen is providing a framework, and their body is moving within that framework. Makes sense. Now let's get a little more abstract. What about physical action on mental objects? This one sounds a bit trickier to grasp.
It does sound a bit out there, but it's really about using physical gestures to represent and manipulate things that we're imagining. The key difference here is that the gestures themselves aren't directly changing anything in the physical world. They're more about expressing and shaping our thoughts.
Okay, so like using your hands to describe the shape of something you're imagining.
Exactly, or like miming an action you're thinking about. The article talks about this really cool study with third graders who are learning about mathematical equivalence, like 2 plus 9 plus 4, exactly. They compared 3 groups. One group physically moved number tiles around, another group used concrete gestures that mimicked that movement, and the third group used more abstract gestures, like just pointing.
So different ways of representing the same math problem. What did they find?
Well, all the groups performed pretty similarly on the specific problems they were taught. But here's the interesting part. The groups who used gestures, both the concrete and abstract ones, were better at transferring that knowledge to new, similar problems. And even more interestingly, the abstract gestures seem to be particularly effective for transfer.
Really? So just pointing, even though it's not directly manipulating anything, helped them understand the concept better.
It seems that way. The researchers think that it's because abstract gestures aren't tied to a specific physical object, so they allow for a more flexible understanding of the concept. They even came up with this idea of concreteness fading, starting with more concrete gestures and gradually moving towards more abstract ones as understanding develops.
That makes sense. It's like you're gradually internalizing the concept, making it more mental and less reliant on the physical action. Okay, so we've explored the 3 combinations that involve physical actions. Now let's shift gears and talk about virtual actions. First up, virtual action on physical objects. This sounds like a bridge between the digital and the real world.
It is. And the most striking example is probably robotic surgery, like the Da Vinci surgical system. Surgeons sit at a console manipulating controls with their hands and fingers, but those virtual actions are translated into incredibly precise movements of robotic arms and instruments that are actually operating on the patient.
Wow, so it's like a high-tech puppet show, but with real-life consequences.
In a way, yes. And those systems can even allow for movements that are more precise or have a greater range of motion than what human hands can do on their own.
That's amazing. So you've got the surgeon's virtual actions directly controlling real-world tools.
Exactly. And training for robotic surgery is this whole fascinating process. It starts with virtual reality simulations, then moves to practice on inanimate models, that's called dry lab, then on animal tissues, wet lab, before finally moving to operating on human patients. One of the really interesting challenges in this field is figuring out how to measure improvement in a surgeon's performance, given how much variation there is between different surgical cases and patient conditions. It's not like a standardized test where everyone's doing the same thing.
Yeah, every surgery is unique. Okay, how about virtual action on virtual objects. This
Yeah.
one feels like the most familiar, right? It's how we interact with computers most of the time.
It is. It's using our fingers or a mouse to manipulate things on a screen. The article uses the example of designing virtual science experiments. You might be testing how different weights affect a virtual spring or building and testing virtual toy cars. And studies have shown that learning experimental design in these virtual labs can be just as effective as using real physical materials. Plus, they have some obvious advantages. They're portable, safe, cost-effective. You can often get dynamic data feedback in a way that's hard to replicate with physical setups.
So it's like designing a virtual car can teach you just as much as building a real one, but without needing all the materials and space and potential hazards.
Right. And you can experiment with different designs more quickly and easily. Okay, now for a really interesting one. Virtual action on mental objects. This one feels a bit more mind-bending. It's like using the digital world to shape our internal understanding.
I'm intrigued. What kind of examples are we talking about here?
One really compelling example is using video games to teach navigation skills to people who are blind. The article talks about this thing called the audio-based environment simulator, where learners navigate a virtual building using only non-visual cues, like changes in sound intensity, to create a mental map of the space.
So they're not interacting with physical objects or even seeing the virtual environment, but they're still building a mental representation of it based on their virtual experience.
Exactly. And studies have shown that people who were allowed to freely explore the virtual building in this game format were actually better at finding shortcuts in the real physical building afterward compared to those who are guided along specific paths in the virtual space. It seems like the active engagement, the freedom to explore and make their own discoveries, fostered a more adaptable and useful mental representation.
That's amazing. It
Yeah.
really shows how powerful our virtual experiences can be, even when they're not directly tied to the physical world. Okay, we're in the final stretch now. Let's talk about mental actions, starting with mental action on physical objects. This sounds like something straight out of science fiction.
I know, right? The article does make a little joke about telekinesis, but then it gets into the real-world applications, which are still pretty mind-blowing. We're talking about brain-computer interfaces, or BCIs, that can control robotic devices.
Okay, so we're talking about using your thoughts to control a robot.
Exactly. These interfaces work by detecting brain activity, often using something called EEG, and translating those signals into commands for the robot. The principle behind it is something called cortical preparation. It's the idea that there's specific brain activity that happens just before we perform a movement or even have a cognitive thought.
So you think about moving your arm, and the BCI picks up that brain activity and makes the robot move its arm.
It's a bit more complex than that, but that's the basic idea. And there's this really moving study where researchers worked with people with ALS, a very serious motor neuron disease. And even though they had very limited physical mobility, they were able to use a BCI to control a robotic arm to pick up a glass of water just by imagining famous faces that were linked to different commands.
Wow, so even with severe physical limitations, their thoughts could still have a real impact on the physical world.
That's incredible. What about mental action on virtual objects? Using our minds to interact with the digital world.
This is another area where BCIs are showing a lot of promise. Imagine being able to control a cursor on a computer screen just by thinking about it. One of the challenges here is that a cursor can move in 2 dimensions, and it's tricky to translate that complexity using the relatively limited signals we can get from EEG. So researchers are developing these really clever hybrid systems where they combine different types of mental activity, like imagining hand movements and thinking about numbers, to achieve more natural diagonal control of the cursor. So instead of physically moving a mouse, you're using different mental strategies to move the cursor. That's amazing.
And this technology has the potential to go far beyond just controlling a cursor. We're talking about mentally controlled video games, interacting with augmented reality and virtual reality environments just by thinking about moving your hand or body.
It sounds like the possibilities are almost limitless. All right, we've reached the final frontier. Mental action on mental objects. This sounds like pure imagination at play.
It is, in a way. The article focuses on visual simulations, which are often used in sports training. There's this well-known framework called the Pit-Aleph model, which outlines all the key things to think about when using mental imagery for practice.
Pit-Aleph, what does that stand for?
It stands for physical aspects of the movement, environment, task, timing, learning, emotion, and perspective. So it's really about getting athletes to mentally rehearse their performance as vividly and realistically as possible, imagining all the details of the movement, the environment, their emotions, everything.
So it's not just about picturing yourself winning. It's about mentally going through all the steps, all the challenges, everything that leads up to that moment.
Exactly. And one of the key factors here is the athlete's imagery ability, how vivid and controllable their mental images are. Some people are naturally better at this than others, but the good news is that it's a skill that can be trained.
Like anything else, practice makes perfect.
Exactly. The article discusses a study where they had novice golfers practice putting. They compared groups who did mental practice, physical practice, or a combination of both. And what they found was that all three groups had similar accuracy in their putting, but the group that combined mental and physical practice was more consistent. They also seemed to develop more detailed cognitive representations of the task, suggesting that they had a deeper mental understanding of what was involved.
So mental practice isn't just about visualizing success. It's about building a richer, more detailed mental model of the skill you're trying to learn. Okay, we've made it through all 9 cells of this 3x3 taxonomy. Now, the article goes on to ask this really interesting question. Are the principles of learning universal?
Hmm.
Or do they change depending on whether we're using physical, virtual, or mental actions and objects?
Yeah, that's a crucial point. It's like, are there some fundamental things about how our brains learn that apply regardless of the format? Or do we need to think about learning completely differently depending on the tools we're using?
So it's like, is there a universal learning theory, or do we need a separate theory for physical learning, virtual learning, and mental learning?
Exactly. And the article dives into this by looking at what it calls generic characteristics, which are things that seem to hold true across different types of interactions, and taxonomic differences, which are cases where the specific format does seem to matter.
Okay, let's start with the generic characteristics. What are some of the things about learning that seem to be universal, no matter what kind of actions or objects we're using?
One really interesting example comes from a project called the Animation Tutor. They were looking at students learning algebra, and they compared 3 different formats: static tables, static graphics, and interactive graphics that included virtual manipulatives. You'd think the interactive format would lead to totally different learning patterns, right?
Yeah, it seems like that would make a big difference.
But surprisingly, the types of mistakes students made and how often they asked for hints were remarkably similar across all 3 formats. It suggests that no matter how the information was presented, they were grappling with the same underlying algebraic concepts.
So the format was different, but the underlying cognitive processes were the same.
Exactly. And there's this framework called the Knowledge Learning Instruction, KLI framework, that helps explain this. It focuses on the essential knowledge components needed to master a task, regardless of how that knowledge is presented or practiced. There are also more general cognitive principles that seem to apply across different formats, like Mayer's Select, Organize, Integrate framework, which describes how we process information from various sources. And even basic perceptual factors, like how things are spaced on a page or the direction of movement we make, can affect how we process symbolic information. Whether we're moving blocks around or looking at numbers on a screen, those basic perceptual processes are still at play.
It's like our brains are wired to learn in certain ways, regardless of the specific content or format. But then you mentioned taxonomic differences where the format does matter. When does that happen?
One key area is in the way different formats can support the connection between visual and symbolic representations. Virtual manipulatives, for example, have the potential to really make that connection clear. Like, if you're working with a virtual fraction manipulative, it might visually highlight the parts of a pie chart that correspond to the numbers in an equation. It helps you see the relationship between the abstract symbols and the concrete visual representation.
That makes sense. It's like the virtual format can make those abstract concepts more concrete and easier to grasp.
Exactly. But there's also a potential downside, which the article calls the representational dilemma. Basically, we use representations to help us understand new things, but if the representation itself is unfamiliar or confusing, it just adds another layer of complexity. So how information is visually presented in virtual environments is crucial, and it needs to be consistent across different modules so students don't have to constantly relearn how to use the tools.
So the design of those virtual tools really matters. It can't just be about making things look flashy. It needs to be about supporting understanding.
Absolutely. Another key difference between physical, virtual, and mental actions is how they affect transfer to new situations. While virtual environments can offer these sort of ideal assembly situations where everything fits together perfectly, the article cautions about potential problems with transfer to novel physical tasks.
Like, if you learn to build a virtual car, will you be able to build a real one?
That's the question. The concept of action semantics comes into play here. It's how we understand how to interact with an object based on its properties. Like, we know how to turn a doorknob because of the way it looks and feels. But if you've only ever interacted with a virtual doorknob, you might not have developed the same understanding of how to manipulate a real one. The physical cues and affordances are different. Another important difference is the cognitive load associated with different types of actions. Mental manipulations, especially when there's no physical or virtual presence to ground our thinking, can be really demanding. Studies like Shepard's mental rotation tasks, where people have to mentally rotate complex shapes, show how much harder mental manipulations are compared to physically rotating an object.
It's like trying to juggle balls in your head versus juggling real balls. It's much easier to drop them when you're only imagining them.
Exactly. And this has implications for instructional design. It suggests that it might be beneficial to start with physical manipulations and gradually move towards more mental ones as students develop their understanding. The fact that spatial ability, which is so important in STEM fields, is also quite malleable and can be improved through practice with different types of manipulations is another important difference highlighted in the article.
So it's not just about what we learn, it's about how we learn it. And the tools and formats we use can have a big impact on that. Now, the article briefly compares this 3x3 taxonomy to other ways of categorizing these interactions. It talks about frameworks that focus on the degree of bodily engagement.
Yes, like Johnson Glenberg's 4 levels of bodily engagement with educational technology. Those frameworks help us see where the different types of interactions we've talked about fall on a spectrum of physical involvement. There's also Skomowski and Ray's 2-level model, which is a bit simpler. And interestingly, their research suggests that even restrained forms of physical engagement can be just as effective for learning as more full-bodied activities.
So it's not always about getting kids up and moving around. Sometimes even subtle movements can make a difference.
Exactly. It's about finding the right level of engagement for the task and the learner. The article also discusses Reid's own taxonomy of encoding, which he developed in 2018.
Encoding, what is that?
Encoding in this context is about how information is represented and processed in the brain. It's about the relationship between two things, where information in the first is used by the second. Reid's taxonomy focuses on the types of codes used for input and output: iconic, visual, phonetic, sound-based, semantic, meaning-based, and motoric, action-based.
Okay, so it's about how information is transformed as it enters our brains and how we then use that information to do something.
Exactly. And the article uses examples from the studies we've talked about to illustrate how these different taxonomies can complement each other. Like, using Montessori manipulatives could be seen as motoric input leading to semantic understanding, while playing Wii Sports involves motoric input and iconic visual feedback on the screen.
So they provide different lenses for understanding the same phenomena. All right, we're almost done. What are the big takeaways from this article? What does it all mean?
Well, the main point is that this 3x3 taxonomy gives us a really useful way to think about the interplay between physical, virtual, and mental actions and objects in learning. It provides a middle ground between very specific details about how individual actions and objects are represented and much broader theories like embodied cognition, which looks at the close relationship between our minds and bodies.
So it's a framework that helps bridge the gap between those two levels of analysis.
Exactly. And its strength is that it's really inclusive. It can be applied to a huge range of learning situations, not just in STEM fields. And as we see more and more mixed and augmented reality in education, this framework is going to become even more important.
Augmented reality, that's where you're overlaying digital information onto the real world, right?
Exactly. Like, imagine wearing glasses that show you information about the objects you're looking at, or being able to interact with virtual objects that are superimposed on your real-world environment. It has huge potential for making abstract concepts more concrete and engaging. But the article stresses that we still need a lot more research on how to use these technologies effectively, how to integrate the virtual and the physical in a way that really supports learning. We also need more research comparing learning with physical, virtual, and mental manipulations directly, maybe through larger, more comprehensive meta-analyses. The article mentions Engelkamp's multimodal theory, which suggests that our brains process observed and performed actions differently as a potential theoretical framework for these comparisons. And ultimately, it argues that to really understand how we learn with different kinds of tools, we need to keep exploring these connections across different levels of analysis.
So there's still a lot of unanswered questions, but this taxonomy provides a framework for asking those questions and designing research to answer them.
Exactly. It's a starting point, a way to make sense of this incredibly complex and fascinating area of how we learn.
Well, that was a deep dive indeed. I feel like I've learned so much, but I also have even more questions now. For you, dear listener, as you go about your day, think about the tasks you perform. How do they break down into physical, virtual, and mental components? And could changing the type of action or object you use change how you understand or perform that task? We encourage you to explore the source material we discussed and to dive into the fascinating worlds of embodied cognition and augmented reality. And that wraps up another deep dive, leaving you hopefully a little more informed and a lot more curious.